A pleasant afternoon to all. It is my great pleasure to welcome you to the opening of the OMICSena lecture series. Some of you might have attended first OMICSena last March. That was an information field premiere of the OMICSena platform where DOST-FNI featured the frequently asked questions on nutrigenomics. For the second time, DOST-FNI brings you OMICSena with a bolder move to bring together omics experts from way beyond the Philippine borders. The Philippines continues to build strong innovative foundations, and learning and reflecting from the global scene is a very way to go. As such, we are thrilled to bring you the 9-day OMICSena lecture series. For 9 afternoons, we are expecting to learn the best of omics technologies and how these emerging platforms can enhance nutrition and food research that will eventually be translated for societal benefits of our country. Beyond basics, hopes are high that we can also build networks and collaborative paths, all towards building an omic-driven, innovative Philippines. William Wordsworth said that life is divided into 3 terms: that which was, which is, and which will be. So let us learn from the past to profit by the present, and from the present to live better in the future. I hope that through all the topics to be discussed from this day until October 7, we can learn how to create a better future in life and nutrition through the studies of omics sciences. To all the participants, again, my warmest welcome, and lend us your active participation because we have inspiring lecture series ahead. So thank you so much and stay tuned. Maraming salamat po at magandang araw muli.
Magandang agham po sa ating lahat. OMICSena was coined by DOST-FNRI to create a scene in a good way. It seems that it will continue to serve as a platform for the DOST-FNRI to keep us in the loop on its undertaking in genomics. With Dr. Brian Gonzalez on board, the second OMICSena for 2021 collaborates with the DOST Public Scientist Program to drumbeat the advent of another set of omic science at the Institute, the Metabolomics. This expansion in the R&D platform will guide DOST-FNRI in setting up more actionable strategies in the molecular food and nutrition arena. I am optimistic that the series will provide new learnings to bring stronger and bolder omics-based research and development initiatives, not only in DOST-FNRI, but in the entire country, as I understand that this OMICSena is well represented by genomics enthusiasts mula Luzon, Visayas, at Mindanao. As we come together for the next 9 afternoons, I hope that we will be able to lay out plans and strategies towards the creation of new intervention systems, biomarker discovery, and innovative health and nutrition platforms through the use of omics technologies. May this event sharpen our vision to acquire the lens of seeing through what our country needs to reach zero hunger and optimum health and nutrition at the molecular level. Congratulations to the organizing committee of the OMICSena lecture series and to all the staff of DOST-FNRI led by Dr. Imelda Angeles Agdepa. Magandang agham sa ating lahat.
A pleasant day to all. The Nutritional Genomics Program of the DOST-Food and Nutrition Research Institute is part of the DOST's Big 21 in 2021. This achievement highlights the growing field of nutritional genomics and the DOST-FNRI's New Gen Laboratory now an ISO 17025 certified molecular laboratory. Beyond this recognition, I am more thrilled to see what our R&D program and scientific and technological services in nutritional genomics can offer to ensure optimum nutrition for everyone. Earlier this year, the first OMICSena answered frequently asked questions on Nutri genomics. The first installment of this web-based learning platform of DOST-FNRI's genomics programs made us realize that nutritional genomics can scale up nutrition and health sciences. Studying our genes through the omics platforms can bring about enhanced nutrition recommendations and perhaps nutrition and health policies in the long run. Its eventual integration in clinical practice can boost our efforts to overcome malnutrition and help us achieve our goals of good health and well-being. As DOST continues to expand the country's omics footprint, this second offering of OMICSena with Dr. Brian Gonzalez, our balik scientist for Metabolomics, is anticipated to bring new frontiers in omics-based innovations. This will fine-tune our efforts to use various molecular platforms to pacify and eventually end our long-standing battle against malnutrition and non-communicable diseases. Now, with the generous sharing of information and practices from our keynote speakers ahead of us, I invite you all to join me in getting a detailed glance at omics technologies and how they can play critical roles in nutrition and health. May this deep appreciation of omics technologies guide us in pushing for more innovations directed to our local needs. I am optimistic that this lecture series will also strengthen the competencies of our researchers in initiating omics-based research and development. One thing that the ongoing pandemic has taught us is to hold tight to what science and technology can do. Science and technology will always be an important key in solving various societal problems. Napaghahandaan man o hindi, katulad nitong pandemya, innovations and discoveries will help us thrive and become resilient. On behalf of the Department of Science and Technology, I would like to thank our speakers from different parts of the European Union and the United Kingdom for their time and expertise. I extend my appreciation especially to our DOST Balik scientist, Dr. Gerard Brian L. Gonzalez, for bringing this exciting series to light, together with the DOST Food and Nutrition Research Institute. Thank you all for being here. Let us have a learning-filled week ahead. Mabuhay!
Isang maagham na hapon muli mga kababayan, and to our speakers and viewers from the Netherlands and Belgium, a pleasant morning to you. I am Frances Isabel Hakalan, and I will be your moderator for today's lecture. It is already the 8th day of the OMICSena lecture series. Parang kailan lang po nung tayo ay nagsisimula pa lamang. For those of you who have just joined in, you can still catch up on our lecture series from our YouTube channel. Just key in DOST-FNRI, and while you're at it, don't forget to like and subscribe our channel. This OMICSena lecture series is part of our 75th DOST-FNRI anniversary countdown. We started our countdown last September, and we have 9 months to go before our 75th anniversary next year. As we have been in almost every household of every Filipino, ang DOST-FNRI kasama nyo sa bawat yugto ng buhay at kabuhayan. Today we have for you another exciting lecture on the Nutri and Biofluid Metabolomics to unravel the gut microbiome-diet axis in health and disease. Without further ado, I now turn over the virtual floor to our DOST Balik Scientist grantee, Dr. Gerard Brian Gonzalez, to officially open today's lecture and to introduce our speaker. Over to you, Dr. Gonzalez.
Thank you very much. Maraming salamat, Frances. At magandang hapon ho sa inyong lahat, and good morning to our guest, Professor Lynn Van Hacke. It is my pleasure to introduce to you our speaker for today. Professor Lynn Van Hacke is a full professor and the head of the Lab of Chemical Analysis at Ghent University in Belgium, with also an affiliation at the Queen's University Belfast in the UK. Her team analyzes or performs chemical analysis of food, biofluids, and environmental matrices, the metabolism and biological activity of food contaminants, and the holistic analysis of small molecules through metabolomics and lipidomics using advanced high-resolution mass spectrometry. In the recent years, her team has specific interest in optimizing high-resolution mass spec-based analytical tools, and in recent years, rapid ambient ionization-based fingerprinting to explore metabolic pathways and contribute to early diagnosis, prognosis, prediction, and prevention within the context of food, and more specifically, gut microbiome-related diseases. Without further ado, mga kababayan, maraming salamat po sa inyong patuloy na pagsubaybay. Ikinalulugod ko kung ipakilala sa inyo ang ating bisita ngayong araw, Professor Lynn Van Hacke. Lynn, goedemorgen, welcome.
Good morning. Thank you, Brian, for this nice and elaborate introduction. I'm going to try to share my screen now, and then okay. I'm not quite sure. I don't think it's working yet. For one or another reason.
Yeah, unfortunately, in the Philippines, I think we still need to, the COVID cases are still quite rising. So we'll have to deal with a lot of virtual meetings in the future, like this usually happens. This is normal. So
yeah, we tried it just a minute ago, and then I think now it should be
yes,
fine.
we see the slide. Yes.
Okay, now we see the slide.
Great. Okay. Are you now seeing the full slide?
Yes, beautiful.
Yes.
Okay, great. So I will start. So welcome all to this lecture. Today I'm going to introduce you or give you some more information on what we, particularly at Ghent University, are doing related to nutritional and biofluid metabolomics. And we have a specific focus on unraveling those diseases that are related to the gut microbiome diet axis. So I will give you some practical examples on that as well. So maybe first a short introduction on my lab. So I'm head of the Lab of Chemical Analysis. We are a part of the Faculty of Veterinary Medicine, and we are now also part of a new department, the one of Translational Physiology, Infectiology, and Public Health. At present on my team, we have around 5 postdocs. Tomorrow, one of my postdocs will also be presenting on the DNA adaptomics work she has been doing. We have mutually 13 PhD students and a number of technicians that support the lab. Now, our main research domains are, as said, metabolomics and lipidomics with a focus on health and disease, but we also have some research lines on wildlife reproduction, and particularly the giant panda. It's the work of one of my postdocs, Jella Wouters. Major research line, however, is focus on nutritional metabolomics, and then, as my other postdoc Lieselot will be presenting tomorrow, DNA adductomics, but also a number of analytical, let's say, development for food, environmental and biotechnological applications are a research line that we are pursuing. Now, the main focus within all that research remains to analyze the whole of what we call small molecules, so perform really metabolomics, lipidomics analysis of metabolites and lipids with varying chemical characteristics. Now, what type of matrices do we mostly analyze? We have a number of methods in place for the different biological matrices. So for the typical biofluids, urine, blood, but also stool, saliva in recent years, tissue analysis, but we also have run a number of analyses on food samples, such as tomato, rice, seafood, insects even, and so on. At the equipment side, we are mostly specialized in using high-resolution mass spectrometry systems. We used to have, as a first in the Benelux, an Exactive, the first Orbitrap system. That one was recently removed from the lab. We have now the new Exploris 120, and we also still have our Q Exactive. That is a bit of the main working horse of our metabolomics analysis. For specific quantitative analysis, we have a triple quad. We used to have also the ion trap for more identification and another type of detectors to do quantitative analysis, such as fluorescence. Now, another, let's say, research line that we have invested in recent years is the rapid evaporative ionization mass spectrometry, the REAMS analysis. It's in fact a QTOF instrument that applies a specific source that enables ambient ionization. I'm not going to go too much in depth now. I will go into that later on during my presentation. So all of these instruments allow us to do what we call the holistic metabolomics lipidomics analysis, or specifically the high-res instruments. Now, maybe it's something that has been, let's say, discussed already earlier this week by some of the other speakers. But of course, in metabolomics, it's important, especially when you go towards nutritional metabolomics, that there are what we call integrative actions, that, let's say, the community gathers its expertise around that and sort of compiles documents that can aid other researchers to move forward in the field. And that's what we have done in light of the Foodball project. It was a huge European project with a lot of partners involved, where we drafted this document as an integrative action to show how nutritional metabolomics and what particular parts in that nutritional metabolomics are important. And that's also, let's say, the different parts that I will be going over today to show you what particular aspects you need to take into account when developing metabolomics methods and when applying nutritional or biofluid metabolomics. Now, let's start with a number of our methods and how that developments have evolved and how and what different parameters are important there. So how do we perform metabolomics? As said, we have a multiple matrix set of methods in place, but we have mainly been focusing on those methods of which we believe that they are relevant in terms of their interaction with the diet and the microbiome. And we have also shown, I will show you the results thereof later, that these matrices are particularly rich in metabolome composition. So we are working mostly in our lab on stool and in recent years also on saliva, because of their direct link to gut imbalances, gastrointestinal imbalances, and the diet and microbiome. So developing methods for these matrices encompass making sure that the whole of metabolites and lipids that are present in those matrices are captured in a decent way. And that is, of course, something that is also lined out in the review we have written on that, depending on what particular analysis you want to move forward to. In general, when doing, for example, biomarker studies, untargeted analysis is the type of analysis you prefer because it's unbiased. You're trying to measure everything that is present. And for that, a whole lot of different instruments can be used. But of course, it can be interesting too when you know which specific metabolites you want to measure, such as, for example, short-chain fatty acids or sugars, that you develop a targeted method. And depending on those methods, different tips and tricks, different strategies need to be put in place. To explain that a bit more in depth, how can you see this truly targeted analysis as compared to suspect or untargeted analysis? Well, a targeted analysis measuring, for example, one particular or a list or metabolites really implies that you're like fishing for a particular fish. You know what you want to get. You have a predefined list of compounds. You have your masses, your retention time, potentially your isotope profile. While in suspect analysis, it's more about everybody looking for its own fish. You have specific information on what you want to find, but it's still not, let's say, fully sure what you will be detecting there. You have a database with information and you know what will be, let's say, searched, but there's still a level of unsureness that is not related to or is different than the targeted. And then, of course, you have your fully unbiased, untargeted approach, where you just like with a big net capture whatever is present and then use a top-down approach to determine what is relevant for your particular case. So that's how I usually explain also these different strategies that we use in mass spectrometric analysis. Now, depending on the type of strategy we use there, we have different analytical tools that can be applied. For the quantitative analysis, for the targeted analysis, we mostly use, or the preferred technology is mostly the quadruple or the triple quad technology, because that is a technology that is still the preferred one for truly quantitative analysis. If you want to determine concentrations of known, predefined, targeted metabolites. While when moving forward to untargeted, to true holistic metabolomics, this high resolution mass spec technology is the one that might be preferred. Of course, you have the time of flight alternative as well. We show here the picture of the Orbitrap, but in terms of high resolution, Orbitrap is still the one with, let's say, the truest, highest resolution, and that's why we mostly work with Orbitrap technology. So with that type of technology, you can capture what we call a virtually unlimited number of compounds in a semi-quantitative manner, although there are possibilities to move towards quantitative analysis too, once your specific metabolites have been characterized. Now, a very important part in the metabolomics analysis, and that's a part that I won't go too much in depth on, because I know you had some talks earlier this week of people that are more, let's say, experienced in the true statistical, bioinformatic data analysis than myself, is of course the data analysis. And there are different parts in that data analysis that are relevant. You have, first of all, your research design that needs to be build in a way that it really supports the research questions you want to target with your metabolomics analysis. Of course, then your data need to be generated depending on the technology that you are using, LCMS, GCMS, NMR, other metadata, medical data have to be or must be, let's say, put in a questionnaire or determined in another way. And an in-between step might be the file conversion. We really need to get files that are readable by every statistical program we want to work with. And then an important part of the statistical data analysis work is the pre-processing and data inspection. Once you have pre-processed your data, you can really go towards the statistical modeling and determine what particular metabolites, what particular trends can be linked to, for example, a specific disease. An important last part then within the metabolomics pipeline is to annotate, to determine the molecular structure of your molecules. We can look at trends. You can see a specific trend in let's say, metabolite patterns between healthy and diseased, but you still don't know what molecules, what metabolites are underlying that. And that's where you have to annotate. You have to do additional analysis to determine the chemical structure, the chemical composition of your metabolome. And then, of course, everything comes together when you go and interpret all those data against, for example, nutritional intake, against host metabolism, gut microbiome, environmental factors, etc. And for that, there's a number of statistical methods that can be used depending on the type of strategy you are pursuing. Now, from the analytical perspective, how do we really perform this metabolomics in the lab? And I will give you the fishes example because that's one of the matrices that we have the most experience on. We're also one of the first to have really a validated, both targeted and untargeted method in place. So for fishes, we have optimized the number of dry weight you need for a, let's say, reproducible analysis. And that is preferentially around 200 milligrams. So that's really freeze-dried material. Afterwards, there's a possibility to apply a combination of solid or liquid-liquid extraction, and then we have chromatographic separation in place depending on the type of methodology, lipidomics versus metabolomics. We use the Q-Exactive as a detection tool, and for the full scan detection, so the true omics metabolomics analysis, we use a resolution of 70,000 full width at half maximum. When pursuing the annotation, the identification of metabolites, MS events have to be included, and at that point we use a lower resolution. So those methods can be used to really apply in an untargeted fashion, but a number of analytical standards can be put against that to really be able to do targeted analysis too. And for that, we have around 130 lipids these days and around 450 polar metabolites that we have in-house available, for which the analytical standards can also be added to the analysis platform. Now, just to show you some examples of our methods, so we published the polar metabolomics method in analytical chemistry in 2015, and that one is comprising all the, let's say, polar metabolites going from amino acids over bile acids to different types of carboxylic acids. This method has been improved in the meantime, and I think at that point we had around 200 metabolites that were really targeted in there. By now we have 450, but it also allows you to screen for the whole of metabolites, also the ones that can't be identified, and there we have around 9,000 features. A similar method was developed for the lipidomics, for the lipid part, and there we have a separate chromatographic separation. That one was published in 2017, including all the different lipid MOPS classes as have been described for any biological matrix, in fact. Now, an important part of our work was also to really prove what the relevance was of doing stool metabolomics as a matrix, as opposed to the more classical, let's say, urine and plasma metabolomics. And for that, we did what we call a multi-matrix comparison, where we collected urine, plasma, and stool from 10 different subjects, 5 males and 5 females, to really show how those related to their general composition. And interestingly, there we saw that around 4,000 metabolites were present both in the 3 biofluids, in urine, stool, and plasma. And interestingly as well, stool as a matrix was as good as predicting even differences between male and female as any of the other matrices. And even more interesting, combining those matrices generated even better models. So going towards a multi-matrix platform could be really a strategy, especially when the sample sizes are lower, to have a better prediction in terms of future metabolome outcome, or also in terms of disease clarification. Now, moving forward from there, we then also pursued the development of an analytical method for saliva, because from a gastrointestinal point of view, feces is an interesting matrix, but it's not that straightforward to collect it. It has to happen upon spontaneous defecation, and it's not something that can be collected on the spot. This is similar for urine. Plasma is a relative invasive. You need to sample blood, you need to centrifuge, etc. So saliva would be a really interesting matrix as an alternative, because it can be sampled on the spot. It's painless, easy. There's no, let's say, ethical physiological constraints or whatever. So we started developing a method for saliva, and very interestingly, there was a very rich metabolome also present in saliva, and there was a very nice correlation to stool. And that work was published in 2020. So we also have now a fully validated method for saliva in place, where we have a coverage untargetedly. So let's say the whole of metabolites of around 8,500 metabolites, and also a number of endogenous metabolites that were fully characterized, and that database is growing as well. Now that's the part on the methodologies and how we have evolved our methodologies, or some examples at least. I'm now going to show you some case studies on how we have applied those metabolomics methodologies to really, let's say, solve different research questions in the diet disease range. Now, a first case study I would like to show to you is the work of Caroline Brombout, who did her PhD at my lab. She finalized that last year. And her study was about unraveling the metabolome of, let's say, red meat digest. So really looking into how red versus white meat consumption was different in terms of metabolome. And the main reason for that is because red and processed meat have been linked to specific Western diseases, going from colon cancer over cardiovascular diseases, but also diabetes type 2, while this is not the case for white meat. So we had a number of studies during her PhD. First was an in vitro study where we digested chicken and beef with 10 different, let's say, fecal inocula, fecal bacterial cultures from different persons. And there we retrieved that there were a number of metabolites that could be found when digesting beef as opposed to chicken. And those metabolites could also be mapped within specific molecular processes that have been or that could be linked to specific disease processes. So to give an example, one of the main metabolites that we retrieved, and I will go further into that later too, was 3-dehydroxycarnitine. 3-dehydroxycarnitine is a microbial metabolite that has been linked to cardiovascular disease and is also a precursor of trimethylamine N oxide, also a metabolite that is of interest these days because it has been linked to several diseases. So that was one interesting finding aside from the other ones that are shown here. Now, we also pursued that particular study, that particular PhD with a pig study. And then there was also another PhD student that started on that. We used the pig as a model for human consumption because the pig has a gastrointestinal tract that resembles quite well that of humans. And it's a lot easier to provide the pigs with a standardized diet as opposed to having a follow-up there. And we also have the opportunity to really go in depth and analyze all kinds of matrices. So we analyzed within that particular study the gastrointestinal content, the small intestinal and the colonic content, and we really saw a nice discrimination in the metabolome in between the different diets. So we had a recommended diet rich in vegetables and fruits that was amended with red meat, the same but then with chicken meat. And then we had a Western type diet, high in, let's say, low palatable foods, high in sugars and lipids. So it was nice to see that, particularly also in the colon, the different types of diets could be nicely clustered against one another when looking into the metabolome, and even reaching a predictivity in this case of 0.7 and a very good error score. I was muted. I don't know what happened.
Okay, sorry about that. Can you proceed now, Prof?
Yes, okay. Okay, so, and then aside from just mainly mapping, let's say, the whole of metabolites in these fingerprints, we also try to identify the annotation part, as explained earlier, what metabolites were present in those different diets. And interestingly, we could retrieve also in this pig study the 3-dehydroxycarnitine metabolite, particularly in the red meat diets, the one that we found earlier in the in vitro diets too. And this was the work of Sophie Goethals, who also continued the PhD work of Caroline on this. This work was also also published relatively recently. Aside from the red meat metabolites, we also found a number of white meat metabolites, the anserine and the methylhistidines, metabolites that have been linked or were linked to white meat consumption earlier. And very interestingly, we could also identify a number of metabolites that were specifically present in the Western diet combined with the red meat diet. And those metabolites were certain medium and long chain acylcarnitines. And as you might or might not know, these acylcarnitines have been linked to specific Western diseases before, aside from also specific esters and fat components. So that was also an interesting result, let's say, in terms of finding out what metabolites could be linked to those dietary compositions, and then also could translate it to microbial composition in relation to health status. Now, aside from the matrices that were screened, let's say, really in the gut, we also had some tissue analysis, and that was then the work that Caroline also pursued. And interestingly, also in the tissue, we could retrieve the similar metabolites that were found in vitro and in the biofluid. So also the 3-dehydroxycarnitine and its metabolites could be retrieved in those tissues, and we could really confirm the hypothesis that was put forward, that this metabolism on the 3-methylamine oxide might be linked to the red meat consumption and the processed meat consumption. We also did additional in vitro experiments to really confirm that those metabolites were formed upon microbial transformation. So it's really the intestinal bacteria inside, in this case, the in vitro systems, the pig study, and we also had an additional rat study to confirm that are responsible for these transformations, and that might be linked to some of the risks that can be related to red versus white meat intake. So this work was also published very recently, only a couple of months ago. I don't know what happened, but there's like yellow lines that are appearing on my screen while I'm not doing anything to cause that. Is that, and there is somebody drawing on the screen, or I think it's Anel Estivel it's mentioning. Could you remove that, or because it's not really a...
Yes.
Yes. I'm sorry. Apologies for that, Professor Lin. We'll try to control. We'll try to control the access of the participant.
Yeah, and could we remove those lines? Because I have the impression when moving forward to the lines, those lines.
Yes.
Yeah.
Hold on a minute.
Let's take a 1-minute break to remove them first.
Yes.
It also happened yesterday.
Okay.
Hold on. Okay, apologies. So our technical team are trying to remove the lines.
Could you maybe unshare first, Lynn, and then share again? Maybe it will.
Yeah.
For everyone's information, our participants, we are being viewed here in Zoom by 171 participants. So it's just 3:30 in the afternoon here, and we have this much participants. We're currently checking how much viewers we have in our YouTube channel.
So I will try to share again now, Brian, or what would you
Yes,
propose?
please. Yes, please.
Yes, please.
I think I think it's fixed more or less. And for the other participants, if you, whatever happened, don't do it. We don't know what happened. Whatever you did, don't do it again.
It was first just one line, and I thought, okay, I can live with one line, but then they started to increase, and it started to.
Well, the good thing, Lynn, it means that somebody was trying to annotate your notes,
Yeah.
so they're attentive, they're listening.
Okay, can you see the presentation again now?
Yes, we can without the lines. That's very good.
Okay, and it's moving forward now?
Yes.
Yes.
Okay. Yeah, just to double check. Okay, so I will continue with the second case I would like to present, and that's on the work we did relating to type 2 diabetes. So after the work on the red versus white meat, we were really interested to study more using our metabolomics on stool and also lipidomics, because it hadn't been, let's say, investigated before, aside from the classical biofluids, to what extent our methods could also separate, let's say, type 2 diabetic people aside from people with a normal glycemic state. And for that, we collaborated with the University Hospital with Professor Bruno Lapau, who had this cohort in place to collect our samples. And this was the work of one of my previous postdocs, Lieven van Meulenbroek. So at that point, we determined a composition, both of lipidome of the polar metabolome of those patients. And in total, we could retrieve around 19,000 and 6,600 lipids and polar metabolites. Aside from that, we, of course, also built what we call the discriminant analysis models to see how well those patients could be separated from their healthy counterparts. And at that point, for the lipidome, we had a relatively good model with a Q-square of around 0.65. But for the polar metabolome, we had an even better model with a Q-square of around 0.7. Both models were also statistically significant. So at that point, we pursued the further identification of, let's say, those metabolites behind that profile that could really separate the diabetes from the healthy, to also mechanistically determine what was going on. We have a strategy in place there where we select the metabolites based on what we call the VIP score, virtual importance and projection, the S-plot parameters, and the jackknife confidence intervals. And at that point, we could retain 173 candidate markers. Now, from those markers, we had a total of 70 that were polar metabolites. Some were elevated, some were lower in the diabetic people. Interestingly, most of those markers that we found in the polar metabolome could be linked to the treatment that is given to diabetic people, and that is metformin. 3 were directly linked to metformin, 6 were what we call source fragments, so formed in the mass spec of metformin, and 13 were metabolites that were formed in the body of metformin. Also interesting, of course. And to show some of those non-metformin markers, we retrieved one that was 2-amino-2-butanol. That's one that has been related to inflammation, and it's known that diabetic people also have an increased inflammatory status in the gut. And then also a medicine that is used to lower blood pressure, and that is generally also given to diabetic people. So also an interesting finding there. Aside from the non-metformin linked markers, we had a number of metformin oxidation products, and indeed it has been shown that metformin easily oxidizes in aqueous, let's say, environment, and that can be related to its antioxidant properties and a sort of part of its therapy. Aside from that, there were also metformin reaction products with dicarbonyls that have been related as having a role in the formation of advanced glycation end products, but also associated with specific vascular complications of diabetes. So also interesting from a biological perspective and the activity of metformin. Very interesting metabolite that we retrieved was a cholesterol metformin adduct. And that had not been described before, but it does support the fact that metformin has been shown to have cholesterol lowering effect. So apparently it binds metformin. We have tried to simulate that under chemical in vitro conditions, but we weren't able to do that. So it must be really a let's say, mammalian or a microbial reaction that is taking place and that is making sure that this transformation product is formed. So all contributing to the working mechanism. So that work, as shown earlier, has been published in the meantime as well. And a third case study I want to show you is the work that we are doing on cow's milk allergy. As you might be aware of, food allergies are really increasing in the last decade, and specifically for cow's milk allergy. That is an allergy that is occurring very early, at a very early age. So it starts even at a couple of months old, and it has some risks because, treatment might be anaphylaxis. And aside from that, children that are given substitutes, they have the risk of also developing growth shortage and things like that. Diagnosis at presence of cow's milk allergy is really difficult. You can do an oral food challenge, but it's very dangerous because, of course, you can have this anaphylaxis. And then we have the skin prick tests and the serum IgE, but they have a very high number of false positives. And that's why we started this research project together with the pediatric department of UZ Hospital in Ghent to collect samples from allergic children. I'm not going to go too much in depth in the sake of time, but here you can see the profile of those children with IgE-mediated cow's milk allergy against the healthy children. And we collected both stool and urine during this study. And interestingly, we were able to separate those, and we have some differences in the metabolome that could be promising in terms of future biomarker discovery and new diagnostic tests. Just so to show for the stool metabolome what differences we truly saw, we had, amongst others, increased tryptophan levels, decreased TCA intermediates, very interesting, also a clear allergic inflammation reaction. That's really the most significant one, and it's the piperidone that is the responsible there, but also a decreased alternative bile acid formation with a significant lower presence of specific bile acids in the allergic children. Now, aside from stool, it seemed that for the cow's milk allergy, urine had even better results because the separation for urine was at that point a bit more clear, and also when moving forward to the IgE mediated differences. So also similarly, we have an increase in specific metabolites related to inflammation in urine, a decrease in carnitine levels, and also specific purine and histine metabolism was altered. So I'm not going to go too much in depth here for the sake of time, but this work is still, let's say, under preparation. And we also have microbiome data there. So the final goal of this work is to really integrate the metabolome data that we obtain from the different matrices with that microbiome data. And we are working towards a more of an integrated fused omics approach there to generate the best out of these data. So that's something that will come out normally in the course of next year. And a final case is the research project of Kathleen Wijnand, who is working on the metabolome of obese adolescents. Obesity is, as you are all aware of, an important Western disease that is really growing also in European countries. Highly obese children, but also adults, of course, are at risk of a lot of comorbidities. And there's been a lot of, let's say, research on what are the factors that are mediating the diseased state or the risk to become obese more. And a major factor, and specifically in children and adolescents, is the stress physiology and is how they interact with stress and how that affects their eating behavior. Now, aside from that, obese are known to have a constant state of low-grade inflammation with the gut microbiome as an important factor. And because in adolescents, it's not straightforward to sample any matrix for that matter, but surely not stool. They are a bit reluctant towards that. We decided to work for that cohort with a saliva analysis and do both microbiome and metabolome analysis. So here's some very first results on the metabolome separation between the healthy weight and obese adolescents that we sampled during this study. So there you can see that there is a clear discrimination between the healthy weight and obese in the saliva metabolome, and that's one of the first studies using saliva for this type of cohort, but also a clear separation between what we call the low stress adolescents and the high stress adolescents. Our final goal in this project is to really determine if we can classify those adolescents based on what we call low stress, high stress, obese, non-obese, and if we could link specific stress metabolites to the obesity case and then propose alternative treatments for those children, for those adolescents. But that is work that is still ongoing, and that will come out in the next years as well. Now, I shortly wanted to introduce you also to one of our other platforms that we have been working on in the last years. And that is one that sort of deviates from all the classical metabolomics work, from the conventional workflow, because it allows us to bring metabolomics from what we call the lab side, from the bench, to maybe in the future the point of care environment, or maybe more to practice. Now, as compared to the conventional metabolomics workflow, where we have an extensive sample prep, where an analysis runs around 20 minutes per sample, and where there are high labor and material demands, with our future on-site or point of care metabolomics workflow, there is no sample prep or very limited. We can run a sample in 30 seconds, and we can run in total more than 500 samples a day. It's a very simple workflow where we don't need extraction or chromatography, and it uses ambient ionization mass spectrometry. Here you can see the system that we have in place. In the lab, we have a motorized stage that is cooled, that is directly linked to a laser beam, and that laser beam is used to ionize the molecules inside any biofluid that we can put, for example, in a multi-well plate, as shown here. Now, let's say the ionization plume that is generated directly goes to our mass spec instrument, to the REAMS source, and that REAMS source is connected to a QDOF instrument that generates a fingerprint of the biofluid. We have developed this method for different types of biofluids, for a stool homogenate, for saliva, merely centrifuged, nothing else, urine, no pretreatment, blood, no pretreatment. And there we can really see that we can generate very nice fingerprints, starting from a small volume of only 15 to 100 microliters, depending on the biofluid. I won't go too much in detail on this, but we have a very extensive Nature protocols that has recently been published on our new, what we call ex vivo molecular fingerprinting method, using this LA REAMS system that really allows you to do this rapid metabolomics. And just to show you that this rapid metabolomics, or the future point of care applicable metabolomics, can also be used for the cases that were presented before, just a summary of the methods. So indeed, you can see that we have fingerprints, unique fingerprints for the different biofluids. We have a relatively high number of detected features, not as high as with the classical metabolomics, but still a couple of thousand for each matrix. And also for the majority of metabolites, we really have a high number of compounds that have an acceptable coefficient of variance, so that can be analyzed in a reproducible manner, both in positive or negative polarity for the different biofluids. Now, using the same samples that we analyzed previously with our classical metabolomics pipeline, we have also used our new rapid metabolomics pipeline to analyze or to determine the difference between healthy and type 2 diabetes. And indeed, similar good models could be obtained there. So that was really our proof of concept that the LA REAMS is also an excellent platform to differentiate, for example, between normal and high glycemic state, and can be used as a sort of pre-screening for further in-depth metabolomic analysis. Aside from that, we also tested our LA REAMS method on the urine and stool that was obtained from our cow's milk allergy cohort. And again, similar models, those models are not excellent because there's a big variation in between the patients, but the models that were obtained were similar than the ones we obtained with our classical pipeline. So that's also something that we are studying a bit more in depth now. And then for the last case, for the obesity case, also with our rapid pipeline, we were able to determine or to classify the obese versus overweight versus normal weight in a similar manner than with our classical pipeline. So it's really a promising future strategy to perform rapid metabolomic screening that has the ability to move forward there. Okay, so that brings me to the end of my presentations, where I have some take-home messages and also a hint towards what I think future research should focus on. So I think related to the nutritional or biofluid metabolomics workflow, as you can see, and as you have also learned probably throughout the week, it's a complex process, and it's important to integrate really all the different steps to allow flexibility, to allow you to analyze everything related to the complex biology as good as possible, and it requires these technological solutions. So I'm really in favor of high-res mass spec to move forward in metabolomics. And I also think that combining the metabolome of biospecimens, of biofluids, and really use also metadata on and clinical data together with information on the food metabolome will really help to move the nutritional sciences forward and to aid unravel what we call diet gut microbiome health axis. So I think that now that genomics revolution has fully, let's say, been achieved, that metabolomics is now ready to also bring back the attention to really study metabolism, because of, in essence, metabolites are our directest link to final health outcomes, and most of the markers that are in place in clinics are in fact metabolites. So we should focus more on metabolomics as a technology to move forward in epidemiological studies. So with this, I would like to thank, let's say, all the collaborators in my lab, but also the Institute for Global Food Security, where I'm affiliated to, and all the funding agencies that have provided us to make sure this work was possible. And of course, you for your attention. Thank you.
Thank you very much, Professor Lin, for that very informative, comprehensive, and a complete presentation of the power and the opportunities that lies ahead for metabolomics. It's really nice that to hear and learn new things day by day, and that we can integrate genomics and metabolomics to have a more holistic approach in recommending certain nutritious guidelines or creating policies in the future. So it will really, the point of care is really promising, as it can really be, we can really bring it closer to the people in different areas. Okay, so everyone, can we give Professor Lien Van Hacke a virtual applause? Okay, I gave you a double virtual applause.
Thank you.
All right.
Well, if I may just add, thank you. So in the past 2 weeks, we've all been we've been introduced to a lot of analysis based on blood and urine, and I'm very happy that Lynn has closed the loop, introduced us with the other very important matrix to consider, and that's the fecal metabolome.
And saliva.
And saliva, of course. And which are the, of course, it's the most, it's I think the least concerning of all sampling methods, which is very good. Frances, do we have any questions? Otherwise, I can start shooting my questions.
Okay, we have one now. Sorry, how do I pronounce your name? Is this Geert? Okay.
Geert, yeah.
Okay. So the question is, do you use similar extraction solvents on the different specimens, like stool, urine, or saliva you measure?
Yes, we in fact optimize the solvent composition and there's also the types of solvents per matrix and also per, let's say, type of analysis. So we have different solvents for the polar metabolomics as compared to the lipidomics. And let's say that the composition of the solvents is mostly similar, especially for the lipidomics, but their relative percentage might differ. I think like for the stool, we have 25% methanol versus 75% water, while for urine, that balance is a bit different. I think for saliva, it's just a dilution even, because that showed to be a dilution and a centrifugation. So it's really a very straightforward extraction method.
Okay. We also have another question from Dr. Sofia Amara. Do you have to include genotype information when you analyze dietary metabolites?
Yeah, I think it's an open answer there. It depends on your research question. If for your particular research question, genetic information might be relevant, I do think it might have an added value to include those analyses. I think if you're really studying, for example, the relevance of specific microbiota, it might be interesting to add metagenomics information there or deep sequencing information, but it all depends on your final research question. I think to measure dietary metabolites, if you would, for example, only want to know what the specific intake of a food is, it's probably less relevant. So it really depends a bit on what you want to study.
All right. Okay.
Can I pitch in if while you're looking for online questions,
okay.
Frances? Yeah.
Okay.
So yeah, just on a practical note, Lynn. Of course, I understand that your studies are in collaboration with USET Ghent, which is the Ghent University Hospital. If we are to implement the studies using a national nutrition survey in the Philippines, for example, what would be your advice on how to collect and transport the fecal material? How do we prepare it in the field before it arrives in the lab, because it's not a hospital-based study?
Maybe a first addition is it's not merely USET Ghent. We are in fact also collaborating with USET Brussels, USET Antwerp, USET Leuven. I just to make sure that I don't forget anybody. And indeed, it's a practical consideration. For the stool samples, what we do at present is really advise people to store them at home in their freezer at -18 degrees, that mostly is. And then our PhD students go and pick them up as quickly as possible, or we now work with type of courier that goes and picks up the samples. But in any case, because we know and we realize that this type of transport is not that straightforward, we have some projects going on at present where we are developing what we call sort of swap type devices that stabilize the metabolome. And our future plan would be to use those to collect, for example, a fraction of the stool, or even have an in vivo swap for small children, for example. It's also used for microbiome analysis already with a sort of stabilizing buffer, but that buffer is not good for our metabolomics analysis. So we are really working on developing a specific device there. But since it's been recently patented, I'm not disclosing too much information yet. Yeah.
Well, if any case you need to roll it out in a real field situation, I think we can have a discussion.
That's a possibility.
Professor Lin, can I just ask if that is also the case for saliva?
Yes, that's also the case for saliva. We are what we are developing. It's called the MetaSamp. We have recently have the name branded. We are developing one for urine, for saliva, and for stool. And it's a different composition because the metabolome is different, the matrix is different. So the composition of the sampler should also be devised versus the matrix. Of course, for saliva, transport is a bit less troublesome than for stool because you don't have the icky factor there, to put it that way. So just collecting a couple of mil of saliva in a tube, freezing it, people are less resentless towards that than versus putting a stool sample in their freezer.
Okay, got it.
Actually, I think that poses a quite big challenge, right? If we are to do a field study in a national nutrition survey and we have to ask people to put stool samples in their freezers, that could be off-putting to many participants of the study. So we might have to think of a logistical strategy, how to collect stool samples if in field.
It works in a similar way with the stool samples, and they also ask the participants to collect them at home in the freezer. But yeah, if you would have an alternative, I do think it would be better in the long run.
Or again, this would be an opportunity to collaborate with major hospitals near the provinces and the cities for the storage and the freezing of samples. So again, a lot of opportunities popping up. So there's a question from Professor Maritos Cation from the University of Santo Tomas. Before the question, she said, "Thank you very much for the very comprehensive presentation, Professor Lin. May I kindly ask regarding this, after the discovery of significant metabolites, are there any validation analysis that you also perform to support the findings?"
Yes, of course, it depends on the study. Like in the first example I gave, we first had an in vitro study where we tried to discover the differences between red and white meat metabolites. Afterwards, we confirmed those findings in an in vivo intervention trial in pigs, and we also had a rat study to support that. And in a latest phase, we also measured those metabolites in humans. And a second validation would then be to have those metabolites also measured in a second cohort. The same is true for the diabetes work. There, we had our initial cohort, and now we have a follow-up study in place where we received samples from the Dutch cohort, the Lifelines cohort of diabetic patients to see if we can confirm the metabolite markers we found there. So indeed, it's a very interesting question, and very true that those validation studies are required. But it depends a bit on the type of work, whether for that particular project we have the possibilities to do so, or if we collaborate further on to do so.
Let me check for other questions. Okay, while waiting for other questions, I have one, Professor Lin. I'm just curious about the quality control materials that you use during laboratory analysis. Are these biological in nature, or there are already synthetic materials that are certified as positive controls?
You mean the QCs that we are using? We are mostly using QCs that we make ourselves, especially because when you run a metabolomics analysis, the best QC is still a QC that is in fact an average of all the samples that you're running. Because if you have to continue down with the statistical analysis, PCA-wise, or the modeling, it's better to have a composition that is as close as possible to what you want to normalize, because you're using those QCs to normalize the other samples. So if they have an entire different composition, it's more difficult. So mostly we take a subset of the samples and we make extracts based on a combination of a subset of those samples, or if possible, if the run is not too big, all the samples to use as QCs.
So you're sort of pulling samples, right?
Yes, we're pulling
and
samples.
then how long would be the viability of frozen samples?
It depends on the matrix. For the stool, we have also published some work on that. We did a stool storage stability study, and there, depending on the metabolome or lipidome, it's advised not to store longer than 6 months. I think earlier stability studies have been published on urine, and I think for urine it's a bit longer. And that's also why we are now devoting work on making samplers, because that's an additional advantage of these types of samplers, because they bind the metabolites, they reduce the opportunity that metabolites are oxidized, hydrolyzed, or in a different way metabolized by microbiota that are still actively present. So it should also increase the stabilization and the duration of storage, even at -80 degrees, because as you know, any chemical process still proceeds at -20, -80, a bit less, but still. So yeah, it's an issue.
Okay. Thank you very much. So those are duly noted and taken into consideration for future studies. Okay, do we have any more questions? May hahabol pa ho ba? I'm hearing none. Do we have more questions on YouTube? Hearing none. Okay, so again, let's give a virtual clap to Professor Lin for a very, very informative discussion today. Thank
you
you,
very
Prof.
much.
Lin.
You're welcome. Thank you.
Yeah, it's my hope that one day when all travel restrictions are lifted, that we could invite you to fly down to the Philippines to wow us even more with your passion and your research, and most importantly, so we could ask for your wisdom on how to design and better perform our experiments in the Philippines in metabolomics. So with Lynn's decades of experience in metabolomics, for sure we have a lot of insights that we can learn from that and how to perform our studies. So thank you very much again, Lynn, for this lecture early morning in Ghent. So I guess I'll just introduce our activity for tomorrow for everybody to remind us. Our last lecture will be tomorrow. It will be the Dr. Liselot Himmerich, who I believe is here today. I think if Liselot is here, you can say hi.
Yeah.
Okay.
Indeed.
Well,
Yes.
I think yes,
Hi.
there she is. So tomorrow we will be introduced to a mass spec-based analysis on the DNA adductome, and that will be our last lecture for this webinar series. So I hope to see you all again tomorrow. Maraming salamat po.
Okay, thank you, Brian. And this concludes our lecture for today. So I'd like to thank all our participants who joined us, sa ating mga avid viewers from Luzon, Visayas, and Mindanao. We are well represented by hospitals, universities, research institutions. So thank you very much for your continued patronage to the OMICSena lecture series. Join us again tomorrow for another fun-filled learning. And may I remind at this point all our participants to make sure that you have accomplished your evaluation form, the link to which is flashed on your screens now. The certificate of participation will be available once you have accomplished the said form, and you may avail your certificate starting October 20, 2021. So once again, this is Frances Isabel Hakalan. Bye for now, and see you all tomorrow for the final lecture and the closing toast of the OMICSena lecture series. Stay safe, everyone.
Thank you, Lynn. Thank you, Liselot. Bye, everyone.